Hello viewers, welcome to Add-on. In this question we are asked, what do you mean by frequency modulation and explain it with a suitable waveforms. Okay, so let us start with frequency modulation. Now we all know by modulation, the term modulation means it is a technique by which we can send low frequency signal or weak signals to a larger distance, or we can send it from the transmitter to receiver which are present at a large distance apart. Okay, suppose this is a transmitter and this is the receiver. We want to send a weak signal at this point and this distance is very much large. Okay, so if we want to make sure that this weak signal is transmitted from the transmitter to the receiver without any kind of distortion or any kind of uncertainty, we will multiply it with a high frequency signal or a strong signal, right? Because suppose this is a sinusoidal signal, this is a this is the original message signal that needs to be transmitted, which is represented by m of t, and this is a high frequency signal or a strong signal that needs to be multiplied with the message signal in order to transmit it over a long distance from the transmitter to receiver. And this high frequency signal is known as carrier signal, which is represented by c of t. Okay, now this particular carrier signal has three entities. One is the amplitude. Okay, one is the amplitude, one is the frequency, and one is the phase. Okay, so the three entities are amplitude, frequency, and phase. So in order to use this carrier signal to modulate this message signal, these three entities of the carrier signals can be changed. It will be either amplitude, it will be either frequency, or it will be either phase. Okay, so in our question we are asked about frequency modulation. So in frequency modulation, the carrier frequency will change according to the message signal. So it will be more clear when we look at this waveform. So as we can see, this is the message signal, which is m of t. This is the carrier signal, which is c of t. Okay, so how we can know that this is a low frequency signal? So we know f is equal to 1 by t, where t is the time period and f is the frequency. So if frequency is large, then time period will be less, and if frequency is less, time period will be large. Okay, so we can see here in this signal the time period is this much, which is t, for the positive half cycle. Okay, and in this signal the time period is this much for the positive half cycle. So if we look at it by our bare eyes, by our naked eyes, we can easily identify that this time period is much greater than this time period. So the time period of this signal is much high. So if the time period is high, the frequency will be less, and if the time period is less, the frequency will be high. So this is the low frequency signal and this is the high frequency signal. Okay, so what happens in frequency modulation is that the frequency of this carrier signal, the frequency of this particular carrier signal changes according to the amplitude of this message signal, and it changes like this. Suppose at this point the amplitude is at its peak value. Suppose this value is plus 5 volt, and suppose at this point this is the lowest value, right? This is the positive peak and this is the negative peak. So the positive peak, suppose I am assuming that it has a value of plus 5 volt, and the negative peak I am assuming that it has a value of minus 5 volt. Okay, so the frequency, as I have said, the frequency of the carrier signal will get modified according to the amplitude of the message signal. So at this point the amplitude is highest, so at this point the frequency will be highest. Okay, so in this region, in this marked region, the amplitude is gradually increasing, right? So for this particular portion the frequency will be increasing. Okay, and for this portion, okay, for this portion, from this particular point up to this particular point, the frequency is decreasing because the amplitude is also decreasing, and from this point to up to this point the amplitude is further decreased, so the frequency will further decrease. So the frequency will be maximum at this point and it will be minimum at this point. So this is our frequency modulated signal. I am saying it as y of fm of t. So we can see that at this particular point, if we draw a straight line, the frequency is maximum at this point. Okay, and now at this particular point we can see that the frequency is minimum, right? So this is how the frequency of the carrier signal gets modified according to the amplitude of the message signal, and if we modulate the frequency according to the amplitude of the message signal, we get a waveform which is like this. And this signal, I am assuming that it is y of fm. Okay, so in order to write expression the expression of this frequency modulated signal, we know that any carrier signal, suppose I am representing any carrier signal as psi of t, sorry, psi of t, psi of t is equal to a of cos of omega ct plus theta. Okay, this omega c, this omega c is the instantaneous frequency. Okay, this omega c is the instantaneous frequency, right? And this theta is the slope angle. Now we know the formula omega is equal to d theta by dt. Okay, omega is equal to d theta by dt, or we can say theta is equal to integration of omega, or we can say theta of t is equal to integration of omega dt. Okay, so what happens in the frequency modulation, that let us suppose in the frequency modulation, I am assuming in the frequency modulation omega, as I have said, is equal to suppose let us say the carrier signal is uh, a cos of omega ct, right? So now the instantaneous frequency, which is represented by omega of I, it is equal to d theta by dt. Okay, it is equal to d theta by dt. Okay, so now d theta by dt is equal to omega c plus kp into m dot t. Okay, so I know that this will be a little bit unclear at this moment, but let us just say we are assuming it for time being, and we will understand it, and we will understand it eventually. So we can say this is the omega I here, this is the omega I, which is equal to d theta by dt, right? So we can write we can say for frequency modulation omega I of t is equal to omega c plus kf into mt. Okay, so omega I is equal to omega c plus kf into mt. So we can write phi of fm, psi of fm is equal to a cos of omega ct plus kf integration of minus infinity to t m of alpha into d alpha, where m, this is the message signal, kf, kf is the frequency constant, and omega c, it is the frequency of the carrier signal. Okay, now the question arises, how do we get all of this, right? So this is the main question that arises here. Okay, so the first scenario that I have said, omega instantaneous frequency, which is omega, is equal to d theta by dt. So theta t, if we do the reverse integration, we will get minus infinity to t omega of alpha into d alpha. Okay, so this theta t is a crucial part in our case. Okay, because we can write this theta t is equal to omega ct plus kp of mt, where kp is just a constant and omega ct, this is the omega c is the carrier frequency, and t is the just our time period. Okay, so if we use this theta, this is the angle, so we can say it is the angle, or it is the we can say that it is the phase. Okay, so this is our main relation, theta t is equal to omega ct plus kp of mt. So if we use this theta t, we will be getting our phase modulated signal, right? But we need our frequency modulated signal. So to get our frequency modulated signal, what do? We will derivate it. Okay, we will derivate it with respect to t. Now if we derivate it with respect to t, what happens? D theta by dt, if we derivate it, find the derivation of it, d theta by dt is equal to omega. If we find the derivation of this term, what we get? We get omega c. And if you find the derivation of this, kp is a constant, so it will remain the same. and suppose the derivation of m of t is m dot t. Okay, we are representing the derivation of m of t by m dot t. Okay, so now what happens, this is the instantaneous frequency, which is omega I. So now I am writing omega I is equal to omega c plus kf into mt. Okay, kf into mt, we have just replaced kp into m dot t by kf into mt for our convenience. Now if we write this frequency in our carrier signal, which was this, okay, we will get our frequency modulated signal, which will be a cos of omega ct plus, what do we get for theta? This is our omega I, right? This is our omega I. So if we want to get theta, we will integrate it, right? We will integrate the above. So if we integrate the above, we will get integration of m of t. So our signal will be a cos of omega ct plus kf integration of m alpha into d alpha. Okay, so I guess we have all understand the concept of frequency modulation. Thank you.